Hi, I'm Valentin Wüstholz and I'm a researcher at Consensus. Today I present to you our work on targeted Greybox fuzzing with static lookahead analysis. This is joint work with Maria Christakis from MPI SWS. What is targeted Greybox fuzzing? Let's look at classic Greybox fuzzing first. It's an automated test case generation technique that uses code coverage feedback to guide the testing process. The goal behind targeted Greybox fuzzing is to focus on executions that reach certain target locations in the code. Examples would be newly added code or code that results in static analysis warnings. The main challenge with this type of fuzzing is that it's difficult to predict if an input is close to target locations. However, such feedback would be very useful to guide the fuzzer. In this work, I present to you a new type of analysis that allows you to compute such feedback. On the left-hand side, you can see the fuzzer. It takes as input a seed input and target locations. It produces as output a test suite that is stored in a queue. New inputs are added to the queue whenever they achieve new coverage. When this happens, we run our so-called lookahead analysis. This is a static analysis that runs online for the given input and produces feedback that can then be used by the fuzzer. Let's look at this in more detail. On the right-hand side, you can see the part of the execution tree of a given program. You can also see in bold the path explored by the newly added input. The goal of the lookahead analysis is to compute the shortest so-called no target ahead prefix. In this case, this is the path pi pre. Since once you reach the program point pi, the so-called split point, all paths that follow the prefix are not able to reach any target locations. The analysis also computes a set of so-called split points along this prefix, namely P1 to Pi. On a high level, this analysis searches for the first split point, Pi, without targets ahead, and it does this in two steps. First, for a given split point, it computes the post condition of the prefix P pre. And it uses this post condition then to perform a more classical reachability analysis that starts from the split point Pi and looks for reachability of target locations when starting from an initial condition of phi. As you can see, this analysis is partially path sensitive, since for the first step we essentially analyze straight line code. This makes the analysis more precise since we avoid operations like joins that typically reduce precision. We can also be sure that the prefix is actually feasible since the fuzzer actually generated an input that explores it. However, we need to be careful with this analysis since we run it many times and we need to make sure it's a lightweight analysis. So here you can see the classical Greybox fuzzing algorithm, and let's see how we extended it to support this type of analysis. The classical algorithm will select a new input from the queue and will assign some amount of energy to it. The amount of energy determines how often it will be fuzzed. When we fuzz the input I, we get a new input f, and when we run it on the program, we get a so-called path ID. This basically tells us which path was explored, and we can add an input to the queue if we haven't seen this path before. The first extension of this algorithm is that we add the lookahead analysis. This happens here when we find a new input. We use the information or the feedback that is computed by the lookahead analysis to then assign energy in a more clever way. Let's look at this in more detail. As you can see from the previous description, all inputs in the queue have a different path ID. However, they may share the same noTargetAhead prefix. And this essentially partitions the queue based on the noTargetAhead prefix. We use two conditions to determine if we assign more energy to a given input. The first condition is if the input's noTargetAhead prefix has been rarely executed. The second one is if any of its split points have been rarely executed. The intuition behind this energy schedule is that we want to reward discovery of new prefixes and new split points. And this is partially inspired by FairFuzz. We implemented this in a fuzzer for Ethereum smart contracts, and it has two main components. First, there's the existing Harvey Greybox fuzzer, which is part of a commercial analysis platform called MythX. The new component is Bran, and this is a lightweight abstract interpreter that uses a simple constant propagation domain. We validated this setup using 27 real-world benchmarks, and we were able to show that 83% of the challenging target locations are reached significantly faster. The median speedup for reaching those locations was 14x. We also saw that the Lookahead analysis is actually very lightweight. It's roughly 3 seconds per 1 hour of fuzzing. To summarize, I have presented a symbiotic approach to targeted Greybox fuzzing using dynamic and online static analysis. Thank you.